Now that we understand the truth functionality of the negation, the conjunction, and the disjunction, and we also understand how we can derive the conclusion of a valid argument using rules based on that truth functionality, we're in a pretty good position to look at, if you will, some shorthand symbols. What I mean by that is this. There are some expressions that would require a fair number of combinations of negation, conjunction, disjunction. And so the two symbols that we're going to learn in Chapter 7 are provide us with shorthands. So let's go ahead and get started. I'm going to move through the sections that we're covering here fairly quickly, not because the conditionals aren't interesting. They're really interesting. Articles are written on them, books are written on them, classes are held on them, but I want to move through them fairly quickly so that in this chapter, so that we can start working with them in a way that I hope will be productive for you. More specifically, I want to get as quickly as possible to looking at the rules that are governed by these two connectives and employing them in derivations. All right, so first we begin with the material conditional, which has a very specific meaning in logic, but I'm going to kind of fudge that meaning in the hopes that doing so will help you wrap your head around what it is that the logical meaning of the symbol is. So first off, the symbol for the material conditional in our version of the system is the right directing arrow. The left side of the arrow is called the antecedent. The right side is called the consequent. We typically articulate the ordinary language expression of the arrow in if-then form. We often, but less often than saying if-then, talk about antecedents and consequents. What we do want to avoid, however, when we're thinking about the ordinary language use of the conditional is imputing to the if side and the then side a sort of causal relationship. That is not what the material conditional articulates. However, as I mentioned a moment ago, what I am going to do is kind of fudge a little bit and capitalize on your seemingly intuitive understanding of the if-then relationship by way of causation, so that you can, like I said earlier, wrap your head around this specialized use. One way that you might want to begin thinking about the conditional is in terms of its truth functional equivalence, namely not P or Q. So let's look at some examples. If there's fire, then there's oxygen. That's logically equivalent to either there's no fire or there's oxygen. Here's another example. If you are a living human being, then you must be breathing. And the equivalent, the truth functional equivalent, either you're not a living human being or you must be breathing. We can also see, looking at our last structure, that if not P, then Q is truth functionally equivalent to P or Q. You might consider the equivalence between the phrasing if not, then, and unless. Here are a couple of examples. If you don't have the discipline to get to work on time, then you'll be fired. Unless you have the discipline to work on time, you'll be fired. Now, notice also that I'm using in these cases future tense. We'll try as much as possible to stick with the present tense, but there is no reason right now why we can't articulate and understand what we're talking about in terms not just of present but also future and past. All right, let's take a look at the truth table for the material conditional. Now I'm going to offer you two ways of thinking about the conditional so that you can, I hope in the end, more easily grasp the truth values. But as I mentioned earlier, I'm going to fudge a little bit. I'm going to rely on your content knowledge as well as some thinking about what implication means in our ordinary sense of that word, in order to help you understand the more specialized sense here in our use of the material conditional. All right, but first, let's remind ourselves that there are 4 possible combinations or permutations of truth values for P and Q. So we have on row 1, P and Q are with the value of true. On row 2, P is true and Q is false. On row 3, P is false and Q is true. And on row 4, both P and Q are false. So notice that on row number 1, when the antecedent is true and the consequent is true as well, the arrow or the material conditional is true. When the antecedent is true and the consequent is false, the material conditional is false. When the antecedent is false and the consequent is true, the arrow is true. And lastly, when the antecedent and the consequent are both false, the arrow is true. So let me start with making a comparison to the concept of validity. You know already that an argument is invalid when the premises are true and the conclusion is false. If we say that row 2 is reflective of an invalid argument, we're saying effectively this: if we treat the antecedent as the premise or premises of an argument, and we treat the consequent as the conclusion of an argument, we see that true antecedent or true premises and false consequent or false conclusion yields an invalid argument. So you know that there is one and one row only on which the material conditional is false, and that's row 2, when the antecedent is true and the consequent is false. So anytime you run up against a true antecedent and false consequence, you know that the conditional claim itself is false on this interpretation of the conditional. Let's also take a look at the ordinary language examples that I have below the truth table. And we'll read through those together, and what I'm going to ask you to do is to rely on your ordinary understanding of implication as well as your content knowledge. So we'll read through each and then we'll break them apart. If San Francisco is in California, then it's in the United States. If San Francisco is in California, then it's in France. If San Francisco is in Massachusetts, then it's in the United States. And if San Francisco is in Massachusetts, then it's in New England. Now, notice that for sentences 1, 2, 3, and 4, as well as for P and Q in our truth table, we are looking at the atomic or simple sentences respectively. San Francisco is in California. San Francisco is in the United States. San Francisco is in California. San Francisco is in France. San Francisco is in Massachusetts. San Francisco is in the United States. And San Francisco is in Massachusetts. San Francisco is in New England. Notice that when you take out the if-then, that special sort of implication relationship that we assign to that language disappears. And that's partly why thinking about the concept of validity is really helpful. Because remember that the only time an argument is invalid is when the premises are true and the conclusion's false. In all other cases, you can have, in other words, true premises and a true conclusion, false premises and a true conclusion, and false premises and a false conclusion. The argument is still valid provided that the structure is correct. But again, let me press on your sort of your intuitions. Answer yes or no to the following. Is it true that if San Francisco is in California, it's in the US? You'd say yes, it's true. Is it true that if San Francisco is in California, it's in France? You would say no, that's false. It's false to say if San Francisco is in California, it's in France. Third, is it true to say if San Francisco is in Massachusetts, it's in the United States? Well, yeah, it's not the case that San Francisco is in Massachusetts, but it's true that if it is, it's in the US. And then lastly, and this is the one that typically feels counterintuitive to us in terms of just reading off the truth table values, is it true that if San Francisco is in Massachusetts, it's in New England? You would say, well, yeah, even though it's not in Massachusetts and it's not in New England, if it is in Massachusetts, it is in New England. Yes, that's true. So that's our truth table for the conditional. Let me offer you a couple of other ways of thinking about the conditional. We oftentimes use the language of necessity and sufficiency. So one of the things you're going to want to think about when we're working on translations, and I'll offer up a separate video for translating conditionals and biconditionals. Here I just offer you a cursory account. You're going to want to bear in mind that that the language that we use is going to dictate what goes in the antecedent position and what goes in the consequent position of a conditional claim. So the phrase only if has a very special logical meaning. The word must is in our ordinary language associated with a necessary condition. Only if is also associated with a necessary condition. If you look below these ordinary language phrases, you'll see that what's asserted to be a necessary condition always goes in the consequent position. A sufficient condition is a condition, on the other hand, that is claimed to be a guarantee for something else to obtain. So when we have the standard if-then relationship, when we say provided that or guarantees, we're looking at a sufficient condition. So the if-then relationship expresses that whatever comes after the if goes on the left side of the arrow. That is, it expresses a sufficient condition. So eating a potato chip is sufficient for something to be in your stomach. Earning all A's in your Philosophy 9 coursework is a sufficient condition for earning an A. Don't ask me why I don't have the rest of that sentence, and I'm not good at using this pen feature in PowerPoint, so sorry, my writing looks terrible. But for those of you who actually work with me in person, you know that my board writing is worse than what you're seeing on the screen here in terms of the pen drawing that I'm working. Anyway, Philosophy 9 is symbolic logic for those of you who are working in a course with a different title, but that is symbolic logic or formal logic. Anyway, so back to sufficiency. Earning A's is sufficient for earning an A in the course. Eating a potato chip is sufficient for something to be in your stomach. And then the last expression, just in case, is probably familiar to some of you, but for most of us it is familiar in terms of our ordinary language, but not in a technical sense. Just in case expresses a necessary condition. A necessary condition is a condition without which something else can't obtain. So we say that oxygen is necessary for fire. Completing all the assignments is necessary for passing the course. But notice that a necessary condition all by itself does not guarantee an outcome. Denying the necessary condition, however, denies the sufficient condition. So more on that in a little bit. Again, there will be a video devoted to translations, but once again, here I just want to give you an overview. All right, lastly, let's move on to the biconditional. As you can see, the biconditional is a two-way conditional. It expresses the following idea. It expresses that you have either both entities, both items, or you have neither. So you've got a left and a right side of the biconditional. So when you're using the biconditional, you're saying that what's on the left and the right side of the biconditional is jointly necessary and sufficient. You have both or neither. You always see Tweedledee when you see Tweedledum, and you always see Tweedledum when you see Tweedledee. You have both or neither. So we use the expression if and only if. Again, more on this later, but for right now, let's look at the truth table, and we'll see that the biconditional expresses truth functional equivalence. Notice that when P and Q have identical values, the biconditional is true. When they articulate, or when you have two different values for respectively P and Q, the biconditional is false. That's because the biconditional says if and only if. Let me write that out for you. So if P, then Q, and if Q, then P. So the biconditional is a shorthand way of asserting this longer sentence. It also asserts, as I mentioned before, asserting that either you have both P and Q or you have neither one. And what I recommend you do is put these sentences into a Boole truth table and notice that the values for this disjunction and for this conjunction are the same as the values for the biconditional, and that's because these are all truth functionally equivalent sentences. So the biconditional is a shorthand way of saying that these two sentences, any old sentence P, any old sentence Q, when they have the same values, are equivalent to each other. Now, one of the things that we're going to want to talk more about when we talk about translation is the concept of conversational implicature. For right now, I'm simply going to say a couple of things about it. We want to make sure that when we move from ordinary language into symbolic logic notation, that we don't make a sentence say something that it's not intended to say. So, for example, you and I know that the sentence, some beagles are dogs, is true. You and I also know that what we want to say is all beagles are dogs. But we have to be careful. Why? Because the structure of the sentence, some beagles are dogs, is not the same as the structure, all beagles are dogs. So what we don't want to do is to assert all beagles are dogs when what we might be required to say is something else, namely, some beagles are dogs. So instead of paying attention to a sentence's semantics, right, we know the meaning of beagles are dogs in the sentence some beagles are dogs is sort of erroneously restrictive, even though it's a true sentence, because we know, well, all beagles are dogs. But we don't want to jump the gun on what we know to be the case. In other words, don't worry about the meanings of the language that we're translating unless we must pay particular attention to that meaning. Instead, what we want to do is focus on what the connectives assert. So think about it this way. When you are looking at the sentence's truth conditions, you are conducting your analysis from that standpoint, not from what that sentence might imply when we're in ordinary conversation. So the sentence, unless you study hard, you won't learn the material, is either it's S or it's not L, which is to say, in terms of truth functional equivalence, if not S, then not L, which is not the same as asserting the two-way conditional, that not studying is a necessary and sufficient condition for not learning. And that's sometimes what we imply when we say, unless you study hard, you won't learn. We sometimes infer from that sentence that what the person means is that not studying is going to guarantee not learning, and not learning means you don't study. But that's not what the sentence actually says, right? The sentence actually says S disjunction negation L, which is equivalent to negation S arrow negation L. It's not saying negation S biconditional negation L. With that in mind, take a look at the second example. You pass the course only if you complete the exercises. The sentence, when we assert only if, is restricting ourselves to saying that completing the exercises is a necessary condition. We're not saying that it is a sufficient condition for passing the course. Lastly, just a note about truth functional completeness. We know already, I mentioned earlier, that the biconditional and the conditional are built out of, effectively, or are shorthands, I should say, for a combination of negation, conjunction, disjunction. In other words, the Boolean connectives we learned in Chapter 6 are truth functionally complete. So we can do the work that we need to do with those and those alone. But as I also mentioned earlier, the conditional and the biconditional are good shorthands for us to use. They allow us to express sentences with shorter notation at times than would be required if all we had at our disposal were those first three connectives. I hope that this brief overview of Chapter 7 is helpful in getting started on the material. As I mentioned before, there will be additional work done on this chapter in terms of a focus on translating from ordinary language into the symbolic logic notation that we've learned, as well as some work in truth tables to see, for example, equivalences. And then we will move on to looking at how we can use the conditional and the biconditional in rules for derivations. That's Chapter 8.